Okay, so you learned in Chapter 1 that there's a hierarchy of biological organization, starting with atoms. Atoms make bonds with each other to form molecules. Molecules, when they're very large, are called macromolecules, which form the organelles and cellular structures, which form the cell. And I emphasize that that part of the hierarchy of biological organization is the emphasis of this course. And that after the cell, cells work together, cells of the same type work together to make tissues and so on. You have to know all those different definitions. But in this course, we're going to start with atom, and we're going to talk about atoms, we're going to talk about molecules, and then where things start to get complicated are the macromolecules. And so this first part of the chapter, if you've already had some basic chemistry, you can maybe turn up the speed on the video. The little settings button, you can turn up the speed and go through it, but make sure that you got everything, but you don't have to go slow. If you don't remember or you haven't had some basic chemistry, you'll want to go slower on this first part. But when we get to the middle and towards the end of this chapter, I think everybody is going to need to go slow and be very sure that you're clear about what it is I'm trying to explain. So Chapter 2, the chemical foundation of life. So what is the makeup of a cell? That's ultimately where we want to get to. Okay, so you have some definitions. Matter, all the stuff in and around us. It occupies space and has mass. I never found that definition very satisfying, but that is the definition of matter. Elements are the forms of matter, the types of stuff. So elements are the types of atoms, the different types of atoms that we have, we call the elements. So you have hydrogen, you have helium, you have boron, carbon. So each of those, so those are called the elements. So the basic unit of an element is the atom. Atoms are, and remember, in the hierarchy of biological organization, they are what will make up the molecules. So molecules have more than one atom connected by bonds. All right, so we're going to start with the atom. So atoms and elements cannot be broken down into simpler substances by basic chemical reactions. So I know that atoms are made up of what we call subatomic particles, but it's very difficult to break apart an atom. So we're gonna just start with the atom as our basic unit of chemistry. And each atom has a chemical symbol, usually the first letter or the first two letters, but not always. So for example, iron goes by a chemical symbol Fe. And you kind of get used to the symbols. When you take chemistry, you get used to the symbols. So iron is Fe. So that's iron. Let's see. Magnesium is not Ma, it's Mg. So not always the first two letters, but you kind of get used to it. But a lot of times it is just the first letter or the first two letters. And for the four most common elements, the most common types of atoms in living organisms, which is what in biology we're concerned with, are really these four. These are the four. If you know these four inside and out, you will be in really good shape for your organic chemistry and biochemistry. I mean, this is a real starting place for those types of things. So we're going to focus a lot on oxygen, carbon, hydrogen, and nitrogen. And here are the symbols, O, C, H, and N. A huge amount of, and we're going to think about life here, a huge amount of humans are made up of these elements. So when you add those percentages together, you get, let's see, 96%. So 96% of a human are just these four elements. So that's why I say if you know these, you have a very good foundation. And what I mean by know these, we want to talk about how each of the atoms, how oxygen, carbon, hydrogen, and nitrogen are, what is their structure, because an atom has a structure. Okay, so an atom is the smallest unit of matter that has all the properties of the element. An atom has two regions, the nucleus. Now this can be a little confusing because the atom has a nucleus, and on a different level of biological organization, we talk about the cell. The cell also has a nucleus. But these are two uses of the word, but they mean different things. The atom's nucleus is the center of the atom. Atoms are so tiny. A cell's nucleus is not always, but often somewhat in the center of the cell. Sometimes it can be pushed to the side a little bit, but we will be able to see under the microscope. When we look at some microscopic images, you can see under a microscope a cell's nucleus. It's very difficult to see visually an atom, and you have to have super duper expensive machinery or equipment we certainly don't have here at the college. But so an atom's nucleus is what we're talking about in this chapter, and that's where the protons and the neutrons are located. So these are the smaller tiny particles that make up one atom. And then outside, somewhat outside or at a distance from the nucleus, you have electrons. So the protons and the neutrons, these are our particles. They are kind of bunched together in what is the center of the atom. And then the electrons are whizzing around at a certain distance around that nucleus. So that's really how the atom is set up. And so here, protons, neutrons, and electrons are called subatomic particles. Sub means somewhat lesser or smaller. So they are the particles of the atom which are smaller. It's the particles that make up the atom. Here's an image. This is kind of what we would call a Bohr image, maybe BOHR. Of an atom. It gives you at least a concept of what an atom would look like if you could actually see the subatomic particles. And so in this atom you have, for example, 2 protons, 2 neutrons, and those are in the nucleus, so those are, like I said, in the center. And then whizzing around, now in this picture it's like a snapshot has been taken and you've captured where those electrons are, but if you took another snapshot a second later, those electrons would be somewhere else. But they always stay within a certain distance of that nucleus. So they have sort of a path that they travel around the nucleus, but they're always moving. So the atom that's shown here is helium. Helium has 2 protons, 2 neutrons, and 2 electrons. Now protons have a +1 charge, so they have an electrical charge, and they have a mass of what we call 1 AMU. AMU stands for atomic mass unit. Another term that we use that's equivalent to AMU is Dalton, named after one of the early chemists. So 1 Dalton is the same as 1 AMU. So if you see a word problem and they talk about Daltons, it's just a unit, but it's equivalent to the AMU unit. And protons are located in the nucleus, which we showed you in this image here. Neutrons have a charge. They're neutral. They have a charge of 0, so they're neutral. They have a mass of 1 AMU, and they're also located in the nucleus. So when an atom has neutrons, that makes it heavier. It doesn't make it have any different charge, but it makes it a little bit heavier. Okay, so, and then electrons have a negative charge. Each electron has a -1 charge. A mass of what we call, usually we say negligible mass. Negligible means it's so small, Negligible, negligible. It means it's so small, it doesn't even matter. I like to think about it as, let's say I'm standing on the scale in my bathroom, and I weigh myself, and of course I weigh a perfect 125 in this scenario. And then I get off the scale, and let's say I put 1 grain of rice on my shoulder, and I get back on the scale. Do you think that now technically I now weigh a little bit more, but do you think the scale is going to even detect it? I mean, it's so small. It's such a small amount, it won't even show up on the scale. So think about, the electrons have a mass. It's just so small that we don't even count it when we think about the weight or the mass of an atom. And the electrons travel around in this area, sometimes called the electron cloud, or what we're going to call it, the orbitals. So the electrons are orbiting around that nucleus in a certain path. We're not going to worry too much about the path. Now I'm going to blow your mind a little bit if you think you know a lot about these things. Neutrons, one neutron can actually be broken apart. Sometimes when I'm trying to write the word neutron, a neutron is actually equivalent to 1 proton and 1 electron. In other words, if you break apart, it's hard to do, but if you're able to burst a neutron, and that's what they do in like super colliders and such, they make these particles hit each other so hard that they break apart. A neutron can, not easy to do, but can break apart into a proton and an electron. So when a neutron breaks apart, if you think about it, a proton has a positive charge, an electron has a negative charge. So if you put those two things together, it has a neutral charge. And then the mass of a neutron is equivalent to the mass of a proton plus an electron, except an electron is negligible, so it's really just the equivalent to the mass of the proton. So that's the real, a little more quantum definition of what a neutron actually is. And in radioactive elements, sometimes the neutrons do break apart and the electron will shoot out of the nucleus of the atom, I should say, and that is radioactivity. If you get hit with all those electrons being shot out, it can actually damage your cells. That's why radioactivity is so dangerous. Okay, anyway, back to the point here. So you have something called the atomic number. That's that's a real thing. Atomic number of an element is the number of protons that an atom of that element would have. And every element has a certain atomic number that never changes. So like carbon always has an atomic number of 6, always. If it didn't have an atomic number of 6, it wouldn't be carbon. If it had an atomic number of 7, it would be nitrogen. See, the number of protons is fixed and defines the identity of the element, of the atom. All right? Now, so atomic number is really the number of protons. So carbon has atomic number of 6. It has 6 protons in the nucleus. But then you have this thing, atomic mass. Now, atomic mass is the mass of the whole atom. Atomic number is just the number of protons in the atom. But remember, there's other particles. The mass of the atom is the protons plus the neutrons. We don't count the electrons. You probably remember they're negligible. So you have in carbon, some atoms of carbon have 6 protons. Well, all atoms of carbon have 6 protons, but some of them have also 6 neutrons. So that atomic mass of that atom of carbon would be 12. Some atoms of carbon have 6 protons and 8 neutrons. and that would be what we call carbon-14, and 14 would be the mass. So different atoms could have different atomic masses, even if they're the same identity, carbon. Some atoms of carbon have 6 neutrons, some atoms have 8. Right. Now, usually there's one version of an atom that is more common. So like carbon-12 is the most common version of carbon on Earth. Carbon-14 exists, but there's not as much of it. And so proportionately, we often think of sort of a certain common type of an atom. But for you learning this for the first time, I'll be sure to tell you that all that you need to know. And then as you go through your chemistry classes, you'll get more used to what the common forms of the different elements are. So sometimes you'll see a chemical symbol, and this is one way chemical symbols are done. And there's a chart called the periodic table that has all the chemical symbols of all of the elements, but this is carbon. So what you typically have on a symbol is the superscript that's sort of up and to the left. That's the atomic number. That's the number of protons, right? Protons. And then sometimes it's a subscript to the left, or sometimes like on this one, it's kind of in the center on the bottom. But that number is the atomic mass. And they wrote mass number, but if it says the word mass anywhere, then it's mass. So mass is protons plus neutrons. So this atom has 6 protons and a total mass of 12. This atom would have 6 neutrons and a total mass of 13. So by subtraction, you can figure out how many neutrons this atom would have. This atom would have to have 6 neutrons because 6 protons and 6 neutrons make 12. This atom would have to have 7 neutrons because 6 protons plus 7 neutrons is 13. And the example I gave you on the last slide, you could have carbon-14, which would be 6 protons and 8 neutrons. So those are all possible. What we call these is these different forms of carbon, the lighter version, which is the most common in this case, and the heavier ones, these are called isotopes. All right, isotopes are just different versions of atoms, some that are heavier than others because they have more or less neutrons. They don't have different numbers of protons because the proton is the number of protons is what identifies the element as being that particular kind of element. So, like I mentioned, when some isotopes, usually the heavy ones, some of their subatomic particles will be released from the atom itself, and we call those radioactive or radioisotopes. These are very useful in research and in medicine. And they're also useful in trying to get estimates, not exact numbers, but estimates on dating fossils, for example. However, all dating, all radioactive dating processes have an error rate, and so usually what they like to do is use radiometric dating with all kinds of different isotopes and see if the data can somewhat agree on an age of a fossil. Usually radioactive dating is not great for anything that's not at least many thousands of years old. So this is the periodic table, and like I said, you have the symbols. So hydrogen is H. The atomic number will be up here, and then there will be the mass number. Now, on the I'm trying to circle that. On the periodic table, what they do is they do a weighted average of all of the isotopes. So weighted average means the most common isotope is counted more than the less common isotopes, and then they average it. So the weighted average will typically be a very strong hint as to what the most common isotope is. So in this case, if you just round this number off to 1, that is the most common isotope. So hydrogen 1. And so what that means is that most hydrogen atoms have 1 proton, and their whole mass is 1. That means they have no neutrons. That's the most common form of hydrogen. No neutrons is what I'm trying to write here. You can write no neutrons on your paper. So earlier I mentioned this concept of the Bohr model, BOHR. You have, for any atom, a lot of times what we do is we have, they don't even usually draw a circle, but in this case they drew a circle. They have the symbol of the element here in the center, and that represents the nucleus, since they don't really mark how many protons or how many neutrons in this drawing. Because the Bohr model is focused on the number of electrons and how the electrons are distributed in the orbitals. Now, the Bohr model is not very realistic. In other words, this is not actually how the electrons travel around the nucleus. Some of the electrons do travel in perfect spheres around the nucleus. Others travel in like figure eights, or maybe you could think of dumbbell shapes. We're not going to try to, for our purposes, it's not going to matter. But I just want you to realize the Bohr model is a simplistic model, overly simplistic model. When you get into chemistry, they'll expand it into the more correct model. But for us, we just want to kind of get a general idea of what how the electrons are laid out. If an atom is neutral, and most atoms you can assume are neutral unless you're told that they're not, or unless the symbol of the atom has a plus sign or a minus sign on the symbol, then that means it has a charge. But if there's no sign, no plus or minus on the symbol of the element, then it's neutral, meaning it has no charge overall. What that would mean is that the number of protons in the nucleus of each atom matches the number of electrons in the orbitals. And so it cancels out the charge. If you had 3 protons in the nucleus, then you have 3 electrons, and that cancels, those charges cancel each other out. And what happens is in the simple model of the atom, the Bohr model, you have these levels. We could call energy levels or electron shells. So what did she wrote? She wrote energy shells. So energy levels would be another way of saying it. Energy levels or electron shells. These all mean the same thing. So when somebody's talking about energy levels, energy shells, electron levels, what they're talking about is electron shells. Is this kind of concept in this picture. So the first shell, the one that's written 1N, the first level is that zone where electrons can be, and in 3 dimensions, you think about it all the way around. And the electrons are at a fixed distance from the nucleus, and they're traveling around in that space. But that first shell, that first area, is the closest to the nucleus. We actually don't know why the electrons don't just go right into the nucleus, because if you think about it, if there's a couple positive charges in the nucleus and there's a couple negative charges in the electrons, why wouldn't they just come together? We actually don't know. We try to explain it, but it doesn't make any sense. But anyway, this is how it is, not why it is. The electrons travel around the nucleus without collapsing into the nucleus. And the first shell can only hold 2 electrons. It's like there's only enough space, for whatever reason, for 2 electrons to be in that first level. So for hydrogen, remember, hydrogen just has 1 proton in the nucleus and 1 electron in the first energy shell. Simple, 1 proton, 1 electron, that's hydrogen. It's the simplest element of all. You can memorize that one. 1 proton, 1 electron, no neutrons. There are some heavier isotopes of hydrogen, but they're rare, that have some neutrons. But the most common form is by far the 1 proton, 1 electron version. Then let's say you had something like helium. Helium has 2 protons, 2 neutrons, and 2 electrons. So the 2 protons and the 2 neutrons would be in the nucleus. And in the Bohr model, you don't really draw them. The 2 electrons would both be able to fit into that first shell, the one that's called 1n. Now, the next level, when you get to an atom that has 3, so in this, the way that the periodic table is done, if you go across the rows, hydrogen has 1 proton, 1 electron. Helium has 2 protons, 2 electrons, and then that's it for the first row. So you go to the next one, lithium. Lithium is used in drugs for psychotic disorders sometimes. It's pretty hard on the system though, but lithium has an atomic number of 3. So if you had lithium, go back to where I was. Oops, I'm going the wrong way. There we are. So if you had lithium, lithium has 3 protons in the nucleus, so it would have 3 electrons out in the shell. But remember, the first shell can only hold 2. So lithium, you would draw it like this. Lithium, that represents the nucleus. In the first shell, oops, you would have 2 electrons. I'm just going to draw 2 right here. And then, once the first shell is full, then the next shell appears. And the third electron would be alone in on that second energy shell. All right. So the orbitals, the electrons fill the shells in the shells closest to the nucleus first, with 2 electrons filling the first shell. The second shell and the third shell can each hold a max of 8. It can have less than 8, but it maxes out at 8. So once the second shell has 8, the third shell forms. A shell that doesn't have any electrons, you can think of it, it disappears. So the shell only appears when there's an electron in it, at least 1 electron in it. So this is called the octet rule. The octet rule is really about the second and the third shells, not the first. The first only can hold 2. So here's hydrogen. And here's, they don't show really the proton, but it's there. And then here's the electron out here. Here's helium over here. Helium has 2 protons in the nucleus, 2 electrons in the first shell. Now that shell is full. The hydrogen shell is not full. Lithium has 3, so they drew it this way. It's fine. You can draw it any way you want. But as long as I can tell how many electrons are in each shell. And then here is carbon. Carbon has 6 protons, so it has 6 electrons. And so you have 2 in the first shell, and then you see the 4. They've spread apart into the second shell. Fluorine has 9, so you have 2 electrons in the first shell and then 7 electrons in the second shell, so a total of 9 because it has 9 protons. And neon has 10. 10 means 2 in the first shell and 8 in the second shell, so neon has a full first shell and second shell. None of these others, for example, these don't have a full second shell, but neon does. Then when you go, once you have enough electrons that you have to then have a third shell, then the third shell appears. So sodium has 1 electron in its third shell. Silicon has 4 electrons in its third shell. Chlorine has 7 electrons in its third shell. And argon has, they drew this wrong. This is a typo here. Argon has a full 8. Interesting thing about argon, you can spray argon into a bottle of like expensive wine or a bottle of expensive alcohol, and it's heavier than anything else in the air, like hydrogen and nitrogen. So it's heavier because it has more protons, more neutrons. And it's all of these elements here that have a full outer shell, which argon does once I corrected their error. It means it's inert. Inert means non-reactive. So what argon would do when you spray it into a bottle of expensive wine, for example, it will almost create like a barrier on the surface of the liquid so that it can't interact with the air. And it's inert, so it won't interact with the alcohol itself, and yet it's heavier than the air that might be in the bottle. So it's a way of, like, if you have a half of a bottle and it's really expensive stuff, you want to preserve it. They do that in places that have that kind of thing. Anyway, so these elements that have a full outer shell, whatever the outermost shell is, that's inert, non-reactive. These other elements all have room in their outer shell, so they are all reactive. Okay? So all of these guys, for example, are all reactive. So only the inert ones are non-reactive. And what we mean by reactive is that they want to interact with other atoms in certain ways. So the point here is the first shell has 2 electrons. The second shell can hold up to 8. The third shell can hold another 8. So that's the rule. So let me do a little quick practice here. Let's go back to the periodic table. And let's say I gave you something that was not on that chart. Let's say, did we do sulfur? Sulfur has an atomic number of 16. No, not on here. Okay, let's do an example with sulfur. Let's say I asked you to draw the Bohr model of sulfur. Now, I would either give you a copy of the periodic table, or I would tell you that sulfur has an atomic number of 16. So you would be given that information somehow. Then I say draw the Bohr model of the atom. You would do this. You'd put S, sulfur for the nucleus. That represents the nucleus. Then you would draw the first shell and put 2 electrons in it. But remember, if there's 16 protons, there must be 16 electrons to create a neutral atom. So we're going to draw the second shell, and we're going to put 8 electrons in that one. I'm just going to draw little dashes because it's hard to draw with my mouse. Okay, so that's 8 on the second shell and 2 on the first shell, so that's 10. So I still have 6, so I need to make the third shell and do 6. And we usually spread them out kind of in a certain way, but if you don't do that, that's fine. Okay, so what I'm trying to draw here is the first shell has 2 dots, the second shell has 8 dots, the third shell has 6. Okay? And so then this atom is going to be reactive because it still has room in that outer shell. And really all of the elements want to, well, I guess they don't have a brain, but the way chemistry works is that the elements want to be stable, and stable means being inert. So if the way that to become inert is to have an outermost shell that's full. So when things are reactive, it's because they're trying to achieve a full outer shell. Now we usually call the outer shell the valence shell. So valence can be whatever the outer shell is. For hydrogen, the outer shell, the outermost shell is the first shell. So the first shell is the valence shell. For lithium, the outermost shell that has any electrons in it is the second shell. So the second shell is the valence. And for sodium, which is Na, For sodium, the outer shell is the third shell because it has, so that whatever the outermost shell is that has electrons, we call that the valence shell. So the valence shell is different, can be different depending on what atom we're talking about. But each of the atoms is driven, hoping to have a full valence shell. That's what stable is. Stable is having a full shell, and so the reactive elements are going to react in a way to try to become more stable. And the question is, how can they actually achieve that? And we're going to talk about that. Now, I mentioned before, the Bohr model shows the shells as being like perfect concentric circles. It's not really like that. This is really the way that the orbitals look. Some of them are circles, but some of them are more like dumbbells or figure eights, or I don't know what you want to call them, but we're not going to worry about that. But when you get to chemistry and they do show it to you and you have to learn it, then just don't be shocked. Okay, so when an atom is reactive, it means that it wants to achieve a full valence shell. And so it's really all about the electrons, because to get a full valence shell, you have to, there's sort of a give and take of electrons that needs to happen. Okay, and so the protons and the neutrons in the nucleus are not involved in the chemical reaction. Okay, so the way the reactivity of an atom, or what you could call chemical behavior, is only determined by the valence electrons. Okay, so any valence shell that is not full is unstable, or you could think of it as reactive. So atoms will react in ways that try to fill their valence shell. So even though atoms don't have a brain and they're not trying, it's not like they know what they're doing, but that's the way to think about it, is that the atom wants a full valence shell, and it will do almost anything to get it. Some chemical reactions, well, there's always energy in a chemical reaction, and some of them can be quite, there can be a burst of energy. A lot of reactions that happen around you generate a little bit of heat, but there can be chemical reactions that are literally explosive. So those things that's a release of energy when there's a trading of electrons. Okay, so chemical reactions. You have something that looks like this. This is the way we write it. Of course, if I'm mixing it together in a test tube, that looks different, but this is how we put it on paper. This is how we represent a chemical reaction. And mainly we can look at both of these. On this first one here, this is kind of the one I would start with when you're learning about chemical reactions or how to write chemical reactions on paper. We're not going to be balancing reactions. That's something you learn in chemistry, but just recognizing what this is. So you have reactants. That's what you start with. Okay, that's your materials that you're starting with. And then the arrow represents making or breaking of bonds, which really means trading electrons. So there's something that happens with valence electrons. Some are released, some are taken up. I mean, I'm going to tell you what that is in a minute, and then you get the products, whatever is the result. Okay, so reactants and products. The arrow always moves away from the reactants towards the products, indicating it's almost like time. We start and then we end. Start and finish. But what's inside this arrow is what's actually happening. Something's actually happening, and then boom, you have the products. So what's interesting is what does that arrow mean? Like, what's happening? How does that happen? We'll delve into that a little bit. Sometimes you'll see a reaction written this way, And the only way that this is different is that the arrow goes in both directions. And what that means is that sometimes the reaction goes this way, and these atoms become this product. But other times the reaction can go the other way. And so in that case, I'm not sure that these terms make any sense, because if the reaction is going from the left to the right, then these are the reactants and these are the products. But if the reaction is going the other way, then we would call this the reactant, and then the other end would be the product. So it depends on which way the reaction is going. Both of them can be reactants and products in a reversible reaction. So if the reaction is going this way, then the carbonic acid is a reactant, and the bicarbonate ion and hydrogen ion are products. So that's a reversible reaction. Okay. We won't have too many reversible reactions that we'll focus on. So I really, for right now, let's focus on just the basic, simple one-direction reaction. The one-direction reaction can be called irreversible. It can't go the other way. So that would be the one I would focus on right now. Just the very straightforward reaction. So the reactants are what you start with, the products are what you end with. I mean, a lot of times in chemistry, that's what you're doing. I mix, or it's like baking or cooking. I mix these things together, so the ingredients, and then the product is the pie. I have eggs, I have, and in that case, the reactants and then the arrow would be the cooking, or the mixing and the cooking and the, so it's a decent analogy. The reactants are the ingredients, the products is the final outcome after you apply heat and such. So it's kind of an analogy there. And once you bake the pie, you can't reverse it. You can't somehow cool it down and it turns back into eggs and milk and butter, right? Once it's done, it's done. You can't go back. So a lot of reactions are irreversible. Okay, I'm going to take a break and have a second lecture segment that you can pick up with.